Welcome back, focused learners. Okay, so I am absolutely thrilled to jump into today's explainer, mostly because, well, it's the grand finale of our Power Delivery Network, our PDN series. Today, we're tackling a seriously critical transient event, Inrush Current. It's this massive puzzle of physics and timing, and honestly, mastering it is absolutely crucial if you want to protect the functional integrity of your chips. Let's set the stakes here. Imagine you've built this beautifully efficient chip. You've got sections powered down, saving all that energy, but what happens when powering up that sleeping domain instantly crashes your already active logic? I mean, it sounds like an absolute nightmare, right? But this isn't just some hypothetical edge case. This is a very real, very physical threat. If we don't manage exactly how a chip wakes up, the whole system can literally come crashing down. Section 1. What is inrush current? Let's break down the surge. So, by definition, inrush current is that massive, transient current drawn when a previously off power-gated domain, which is sitting at 0 volts, is suddenly connected to VDD. Just think about the physics for a second. That off domain is completely discharged. Suddenly slamming it connected to your main power supply creates this aggressive immediate surge. Why? Because the system suddenly has to charge up all those internal capacitances, the interconnect routing, every single cell node in that block, all at once. The easiest mental model to keep in your head is this. Turning on a gated block is exactly like trying to charge a massive capacitor instantly. When you try to force that much charge into a completely empty space all at the exact same time, you get an incredibly high current. Now, crucially, it only lasts for a very short duration, but it is a sudden, intense spike on your power grid. Section 2, the danger to logic. Let's look at why this inrush is so risky. Okay, so it's really important to understand exactly where this huge surge of current is coming from. Obviously, your primary power supply, the VDD network, is the main source trying to push that charge. But the second source, that's the sneaky one. It's your neighboring ON logic. This causes something we call the charge sharing effect. Your active, humming along logic has stored charge, right? When that sleepy 0-volt domain wakes up next door, physics dictates that charge flows from the higher potential active logic down to the lower potential off domain. So your waking block is literally stealing charge from your working blocks. And that brings us to the absolutely most critical insight for today. Inrush current is not just a power grid problem where your wires get a little stressed out. No, it is a full-blown functional integrity problem. If that stolen charge causes a significant enough voltage drop, a logic 1 in your active block will degrade. It dips way too low, those logic levels get totally disturbed, and boom, you have an outright functional failure in a part of the chip that was working perfectly just a microsecond ago. Section 3. Using power switches. Let's talk about controlling that surge. To safely wake up a power-gated block, we use power switch cells. We've got a header switch that sits right between the main VDD and the gated VDD of the block, and then a footer switch sitting between the block and the VSS, or ground. But the real secret here is the gate control input on both of these. We don't just throw a master breaker and activate the whole domain instantly. No way. We specifically, carefully control these header and footer switches during power on to meter out that current. Section 4, the daisy chain trade-off. Let's dive into sequential enablement. To really grasp sequential enablement, use this intuitive analogy. It is exactly like filling a tank slowly instead of dumping water all at once, right? If you dump an entire bucket of water at once, it splashes everywhere. That splash is your massive inrush current causing voltage droop and logic failure. But if you pour it in slowly, the level rises calmly and safely. We want to gradually charge the domain to keep that peak current way down. And the way we actually achieve that slow pour on the silicon is through a daisy chain setup. The enable signal doesn't just hit all those switch cells simultaneously. Instead, it enters the first one, enables it, and then passes sequentially to the next switch and then the next, with a slight, deliberate delay built right in. We are literally enabling them one by one. But remember I called this a trade-off? Let's contrast the two extremes here. On one hand, if you use a very long daisy chain with tons of delay between switches, your inrush current is beautifully low and completely safe. But your power-up time becomes painfully slow, which hurts your performance. On the other hand, if you just turn all the switches on together, your wake-up time is blazingly fast, but your inrush current is dangerously high and you risk crashing the system. It's the classic engineering dilemma. We have to strike a practical balance between performance and reliability. Section 5, smart mitigation strategies. How do we find that balance? Well, the most common solution is the multi-segment daisy chain approach. Instead of routing one single excruciatingly long chain, we actually divide our driver controllers into parallel groups. The wiring from the power supply splits, and each group forms a smaller, localized chain. These distinct groups then turn on in parallel. It's a super clever architecture because it gives you a much faster wake-up time than a single chain, but crucially, a much lower inrush current than turning everything on all at once. Now, let's get into some actionable, on-the-job training. When you inevitably run into inrush issues in your own VLSI designs, here is your practical debug strategy. First, physically check the voltage droop during the power-up phase. Second, dig into your design and pinpoint the exact switching pattern of your power switches. Third, verify that those switches are actually staggered with the correct delays. And finally, always analyze the behavior of the nearby active logic to make sure they aren't falling victim to that charge sharing effect we talked about. Those debug steps naturally lead into 5 concrete fix strategies. If you find your inrush is too high, maybe because you got a little too aggressive optimizing for wake-up time, step through these. Number 1, increase the delay between your switch enable signals. 2, break those massive domains into smaller, more manageable multi-segment chains. 3, thicken and locally strengthen the power grid routing so it can handle the surge. 4, strategically add decoupling capacitor cells, decaps, to locally supply that transient current so it doesn't drain your active logic. And 5, optimize the physical placement of your switches across the floor plan for a much better distribution. Section 6, PDN Series Wrap-Up. We made it to the end of the series. Just take a quick look at the journey we've been on. We started with the foundational power delivery network and PG grid. We explored the intricacies of power gating and low power cells. We mathematically modeled our voltage drops with IR analysis. We learned to protect our wires from degrading via electromigration, shielded the chip from electrostatic discharge, and today, we finally conquered the transient threat of inrush current. All these explainer pieces fit together perfectly to empower you to ensure total power and functional integrity in modern chip design. I want to leave you with this final, somewhat provocative question to take back to your workstations today. Are you fully validating your chip's transient behavior, or are you just sort of hoping the power-up doesn't crash your system? Look, inrush is brief, but the functional failures it causes, those are permanent. Take these strategies, apply them to your layouts, and design with absolute confidence. Keep learning, keep analyzing, and I will see you in our next explainer.